that is integration, because dm by I is a constant term which comes out of this integration sign. So integration y dA is nothing but the area into y bar. So we achieve total unbalanced force is equal to dm by I into A into y bar. So A is the area of the section above the level EF. Interesting point. Area of the section above the level EF or above the Y1. That means that this area, the hatched area, the hatching area which has been shown over here, area of E, F, G, H, where y bar is the distance of the CG of the area A from the neutral axis. See, CG to the neutral axis. Let us be understood this, what will be the statement y bar on this figure. So this is the cross section. This will be my neutral axis. This is my hatched area which is available y1, and this area is nothing but the area A, and the distance of CG, this is my CG, to this neutral axis is y bar. So due to the unbalanced force acting on the part of the beam above the level EF and between the sections AB and CD, the beams may fail in shear. Clearly visualize that my beam will be fail in the shear because of this net unbalanced force, that is dm by I into A into y bar. This is the total unbalanced force which is acting between these two sections. My beam will be fail at the layer of EF. Hence, in order the above part may not fail in shear, the horizontal section of the beam at the level EF must offer a shear resistance, obviously, because this is the net unbalanced shear force which is acting at the level of EF between the two sections AB and CD. The shear resistance has been applied on that beam to resist the particular value of shear, and our intention is to find out these things. So the shear resistance at least must be equal to total unbalanced force to avoid the failure due to shear, and the shear resistance at the level EF, that is the total unbalanced force, that is the integration of dm by I into A into y bar. So let tau, here the new designation, new term, that is the tau, that is the intensity of the horizontal shear at the level of EF. B is the width of the beam at the level EF. Area on which the tau is acting, that is B into dx. That is the area on which the tau is acting. Shear force due to tau, that is the shear stress multiplied by shear area. The shear stress, that is nothing but the tau. Shear area is nothing but the B into dx, that is the hatched area. Equating these two values of the shear force by equation 2 and 3, we get tau into B into dx is equal to dm by I into A into y bar. So we achieve tau is equal to dm by I into A into y bar by B into dx. Now if we compile together dm by dx together, tau is equal to dm by dx into A y bar into B into I. We know the term, all the term, but the important term dm by dx. Partial derivative of bending moment with respect to the distance x, which gives the value of shear force at that particular section. So tau is equal to FA y bar by IB, that is the basic generalized equation of a shear stress which will be acting at a one particular section. So we achieve an equation tau is equal to Fa y bar by Ib, where F is equal to the shear force at that particular section, while A is nothing but the cross sectional area, y bar is nothing but the distance between the CG of that particular area to the neutral axis, I that is the moment of inertia, and B that is the base width for that particular cross section. So we have an equation that is tau is equal to Fa y bar by Ib, and we have to use these basic fundamental equations in the next preceded sections. So the shear stress given the above equation is the horizontal shear stress at the distance y1 from the neutral axis, but the principles of complementary shear, the horizontal shear stress is accompanied by a vertical shear stress tau on the same quantity. So now, using this basic concept of shear stress by using the basic equation, let us try to solve certain numericals based on this particular concept. Refer the problem number 1 statement. A wooden beam of cross section 100 mm by 150 mm dip is simply supported over a span of 4 meter if the shear force at a section of the beam is 4500 Newton. Find the shear stress at a distance of 25 mm above the neutral axis. A very simple questions which is a direct application of the formula that which we have been derived, and let us solve this simple problem by using the basic concept of this equation. What is the given the data? Let us be understood. First, wooden beam which has been given to us with the cross sectional area. Let us draw a figure on this tabletop. First, they have given a cross section that is 100 by 150 mm and has been stated that it is a simply supported beam. So beam which has been given as simply supported beam, this is one of the section XX which has been given to us. What is the next statement? It has been stated that the span of the beam which is of 4 meter. Next, if the shear force at a section of the beam is 4500 Newton, so at a particular section the shear force value is of given to you 2500 Newton, and the question which has been raised about find the shear stress at a distance 25 mm above the neutral axis. So this will be your neutral axis, and obviously the given section is of rectangle. We know that the centroid which is acting at the CG, so neutral axis is known to us, and our intention is to find out the value of shear stress within this distance of 25 mm. So if you want to refer the figure with this given data, intention is to find out the tau shear stress at a distance of 25 mm above the neutral axis. Let us use the basic equation. Tau is equal to Fa y bar by Ib, where A is the area of the beam above y1. Interesting point. Here the point A, generally it is the symbolic representation of the cross sectional area, but here which cross sectional area is an interesting point, that is above the neutral axis. So if you want to visualize this tabletop figure, then this will be your area. Now this is 25 mm, the available total depth is of 150, this available is 75, 75 minus 25 available is 50. So the area which is available is 100 into 50. This available cross section. that is above the level EF, and here the level EF which is available at distance 25 from the neutral axis. Now Y bar, refer the figure on PPT. The Y bar, that is the distance of the CG of the area A from the neutral axis. Distance of the CG of the area A from the neutral axis means, if you want to refer a figure on this tabletop, the CG is over here and the distance available is this one. And what is that? That is nothing but 50 by 2 plus 25. This is my Y bar. So it is over here 25 plus 50 by 2 as shown on this PPT. I, that is the moment of inertia of the section, and we know that for rectangular section it is BD cubed by 12. B, which is known to you 100, D is known to you 150 cube by 12. We achieve one figure in terms of millimeter raised to 4, that is the equation of moment of inertia of the section. Now our basic equation is FA Y bar by IB. B is nothing but the actual width of section at distance Y1. At distance Y1, the available width is the same width available for a section, because the given section is rectangle. So if you want to visualize on the tabletop, this is the B. This is my B value at Y1 distance. So it is nothing but the 100. So if we are putting all those values on this basic equation, the shear stress tau is equal to 4500 multiplied by the area 5000 multiplied by Y bar 50 divided by the I divided by B value 100, we achieve 0.4 Newton per mm square, that is the megapascal. That is the value of shear stress at that particular section. I wish you have obtained the fundamentals how to solve this problem using this basic equation, that is tau is equal to FA Y bar by IB. Next problem. Number 2. Please carefully visualize the data, read it carefully. The data is over here. A beam of cross section of an isosceles triangle, interesting word, is subjected to shear force of 30 kilonewton at a section where base width is of 150 mm and height is 450 mm. Determine first horizontal shear stress at the neutral axis, second the distance from the top of the beam where the shear stress is maximum, third value of maximum shear stress. The 3 different questions which has been asked on this single question. Let us be understood what the data which has been given to us. A beam of cross section of an isosceles triangle is subjected to a shear force of an 30 kilonewton at a section where the base width is of 150 mm, base width of 150, and height which is given as of 450 mm. Intention is to determine the horizontal shear stress at the neutral axis. So now what is given to us in this data understood with this PPT. A triangular section, the type of beam which not given to us, the base width and the height which has been given to as 150 and this given to as 450 mm. The shear force which has been subjected on this given data is of 30 kilonewton. The question number 1 which has been asked about find shear stress tau at neutral axis. Neutral axis which is available over here, and this distance is of 1/3 h, 1/3 of 450, that is of 150 mm. So available, this is 300 mm. If this is 300 mm, this is my base width. It is how much found out? This has been found out as 100 mm. So if you want to refer the figure, triangular section which has been given to you, and this is my neutral axis position is there. So the first is the horizontal shear stress at the neutral axis. We have to found out the neutral axis of the triangle is at a distance h by 3 from the base, or 2h by 3 from the apex B. Hence, distance of neutral axis from B will be 2 by 3 into 450, that is from the apex, that is 300 mm, and the width available section at neutral axis is obtained from the similar triangles, that is triangle BCD and BNA. If you want to refer triangle BCD and triangle BNA, by taking these similar triangles, the available width at this layer, at neutral axis layer, we can achieve this value as NA by CD is equal to 300 by 450. NA divided by CD is equal to 300 by available total height is of 450. So NA is equal to 300 by 450 into CD. CD value we know, that is 150. By simplifying the simple equation, we got the base width at the neutral axis is of 100 mm. So the shear stress tau is equal to FA y bar by IB, where F is the shear force, that is 30 kilonewton, that is 30,000